In this lecture, let us talk about the spectral properties of polar signaling. As I said, in polar signaling, bit 1 is represented by some pulse, let's say P of t. The P of t can be a rectangular pulse or something like that. And 0 is represented by negative of P of t, like minus P of t. Okay, so bit 1 is represented by P of t and bit 0 is represented by negative of P of t, that is minus P of t. Remember, we have to go to R suffix n. What is R suffix n? Autocorrelation function. Okay, so why do we need this autocorrelation function? Because we need to compute the Sy of omega output power spectrum, and this expression I already gave you this out in the previous class. It is going to be given by P of omega mod square divided by duration of the pulse t naught times r naught plus 2 times summation of r suffix n cos of n omega t naught, where n goes from 1 to infinity. So in order to calculate Sy of omega, I need to know the R0, R1, R2, R3 and so on and so forth. Okay, to compute Sy of omega, we have to go back to the basic expression of this one and look at the amplitudes of R0, R suffix 1, R suffix 2 and so on and so forth. Okay, so in order to calculate the nature of the power spectrum. What is P of omega? P of omega is the Fourier transform of your pulse P of t. Therefore, this Sx of omega, the power spectrum of the pulse, remains the same, but the factor which depends on the amplitude R0, Rn, etc. will have to be calculated afresh depending on the kind of line coding scheme that we have. Okay, so in the polar case, in the polar coding case, your A case, okay, A case are going to be equally likely, like as I said, it takes P of t and minus P of t. Let's say P of t is denoted by plus 1 and minus P of t is denoted by minus 1, right? Therefore, the pulse amplitude will be either plus 1 or minus 1. Okay, and this plus 1 and minus 1 are going to be equally likely. Okay, so the amplitudes plus 1 and minus 1 will be equally likely, that is, the strength of those impulses are equally likely. Therefore, when you calculate AK squared, this will be always positive. Okay, see, from this either AK squared is equal to AK times AK. So I can take 1 times 1, which is 1, or minus 1 times minus 1, then again this is plus 1. So therefore AK square is always positive and which is equal to 1. Therefore, what is the formula to calculate R0? R0 is equal to limit t goes to infinity, your pulse duration divided by t. This is your observed interval. Okay, let's say minus t by 2 to plus t by 2. Within this interval, how many pulses are there? Like this. The duration of the pulse is t naught. So total number of pulses are given by this one. I'm sorry. So this is from the formula. Okay, t naught by t summation of AK squared. Now limit t goes to infinity, t naught by t, AK square, you put k is equal to 1, 2 like that, then this is going to be always 1. Okay, and this 1 occurs half of the time. Not half of the time. How many times it occurs? Whether it occurs plus 1 or minus 1, this AK square is always plus 1. But what is the pulse duration? The pulse duration is t by t naught. This is the total duration t, and in this total duration how many pulses are there? T by capital T naught, where what is a T naught? T naught is the pulse duration. Therefore this T naught will get cancelled, and this T and that T will get cancelled. So this is equal to 1. R naught is equal to 1. Similarly, what are other quantities of interest? R1, R2 and so on so forth. Okay, as I said, this is minus T by 2 and this is plus T by 2, and here the pulse duration is T naught and the interval length is T. Okay, because you may ask a question, how do we get this T by T naught? The total number of pulses in the interval T is T by T naught, and for each of which AK square is always 1. So after summing this up, you will get a total number of total value of T by T naught, and in that it gets AK square is going to be 1. Therefore this has come. So this argument is going to be repeated every time we consider a new line coding scheme, either on-off line coding scheme or polar scheme or bipolar scheme, doesn't matter. So we always try to calculate what is R0, what is R1, R2 and so on and so forth. Alright, what is the product of these two? What is the product of AK times AK plus 1, right? So as I said, AK can take the value either plus 1 or minus 1, plus 1 with half of the time, minus 1 with half of the time. Similarly, AK plus 1 in the next time slot, this are the time slot, it can take either plus 1 or minus 1, right? So again this takes half of the time and this takes half of the time. So AK and AK plus 1 both are independent of each other, independent event. Therefore AK times AK plus 1, half of the time you will get 1, and AK times AK plus 1, half of the times you will get minus 1. Okay, so and this AK times AK plus 1 is equal to 1 because 1s and 0s are random, and now which now becomes 1 and minus 1. Here half of the time plus 1 and half of the time minus 1. Therefore AK and AK plus 1 is equally, you can extend this argument. Okay, AK times AK plus 2, AK times AK plus 3 and so on so forth. So in general I can write AK times AK plus n is equal to either plus 1 or minus 1. Plus 1 occurs half of the time and minus 1 occurs half of the time. Okay, so this is my total duration minus T by 2 and plus T by 2. In that I have so many pulses. How many pulses do I have? Like this, T by capital T number of pulses. So this is total number of pulses. Total number of pulses. Out of this total number of pulses, half of the time I am getting plus 1 and half of the time I am getting minus 1, right? Therefore T by T naught, this total number of pulses, half of the pulses are going to be plus 1. So half of the pulses means 1 by 2 times positive 1. Then total number of pulses, in this half of the pulses are going to be minus 1. Okay, therefore this is T by 2 T naught minus T by 2 T naught. This is equal to 0. Therefore AK times AK plus n is equal to 0. This minus 1 comes over here. So Rn is equal to summation over k, AK times AK plus n. So this is 0. Okay, therefore Rn is going to be 0. That means for any value of n, you take R1, R2 and so on, we can conclude that Rn is going to be equal to 0, and of course n naught equal to 0. Because n equal to 0 we have already seen, okay, that is it is equal to 1. When you substitute n is equal to 0, then you will get r0 is 1. That's what we got it. Okay, which means the second term, that is the summation term appearing in the power spectrum expression, can be ignored. If you look at the power spectrum expression, yeah, this term can be ignored. Only you can consider the first term alone. Okay, therefore your output spectrum Sy of omega is equal to P of omega mod squared divided by T naught multiplied by R naught plus 2 times summation of Rn cos n omega T naught, right? This is the expression. Since Rn is 0, you can neglect the second term. You can consider only the first term. So this is going to be P of omega mod square over T naught and R naught. What is R naught? R naught is 1. Now you may ask a question, why do you assume that there are equal number of ones and zeros? Okay, because 1 is represented by P of t and 0 is represented by minus P of t. And let's say this is my pulse like this, and the amplitude is plus 1. You can take plus 5 also, doesn't matter. Just for simplicity, I assumed plus 1. And minus P of t you can put like this, and minus 1 volt, and this is plus 1 volt. Similarly, you can take minus 5 volt also. Nothing is wrong. Okay, therefore plus 1 is denoted by plus P of t, so this is plus 1. 0 is denoted by minus P of t, minus 1 volt. So 1 is in default represented by plus 1 and 0 represented by minus 1. So therefore these are amplitudes, and these amplitudes are denoted by AK. AK is the amplitude of the pulse, A suffix K, kth pulse amplitude. What is AK? Kth pulse amplitude. Okay, so now why are we assuming this equal number of zeros and ones? For one thing, it is convenient for the maths that we are doing here. But more than that, in reality, we would like them to be like this. Okay, so half of the time it is going to be 1 and half of the time it is going to be 0. Okay, if you take any real source on over a large time period or over a large time interval, we can make an assumption that the source emits equal number of zeros and equal number of ones. And in case if the source is not like that, then we will be converting our data to a form which makes ones and zeros to be equally likely. Because if you don't do that, that means a lot of time you are transmitting redundant information. Okay, if something comes 1 1 1 continuously, that means what you are transmitting redundant information. And if you transmit 0 0 0 continuously, then also you are transmitting redundant information. Anyway, we will talk about that a little later. Okay, we will talk about information theoretic aspects of messages that we want to transmit. So it will always be preferred that we transmit digital data in a form in which ones and zeros are equally likely. If you are not doing that, you are not making the most efficient use of your available bandwidth. Okay, so we will talk about that separately. It is a reasonable assumption. Of course, you may have a situation where in spite of your efforts, they don't become equally likely. And such a situations are likely to be very infrequent and not to worry about too much. Okay, and we can obviously modify any of these results for the situations if required. Now your Sy of omega is P of omega mod square by T naught. Now what is P of omega? As I said, P of omega is the Fourier transform of P of t. And now look at the important thing in this expression. What do you observe from this expression? It has no discrete component. Okay, there is no impulse component, there is no delta function, no delta function. Like unlike the if you look at the previous case like on-off signaling, there we have seen that there was an delta function, so it had a discrete component, but here we don't have any discrete component. Okay, it is only a continuous spectrum. Okay, it is only a continuous spectrum corresponding to the sinc square function. If you use a rectangular pulse, if p of t is a rectangular pulse, then what about your p of omega, your Fourier transform of p of t? It is going to be a sinc function and already have mod square, therefore it is going to be sinc square. So if you use a half width rectangular pulse, half width means what? Half of the time the pulse will be on and half of the time the pulse will be off. Okay, in this time it is on and here it is off. This is 0 and this is t0 by 2 and this point is t0. This total duration is t0. So out of this t0, half of the time my pulse is on and remaining half of the time the pulse is off. So this is called a half width rectangular pulse. Okay, so when I say half width, the implication obviously is half the duration that you can have in that particular interval, which is t0, the pulse is on. Okay, what is t0? T0 is the maximum duration or duration of the pulse. Okay, if you choose p of t to be half width rectangular pulse, then your sy of omega is given by t0 by 4 sinc squared of omega t0 by 4, and this spectrum is identical to the continuous portion of the spectrum of the on-off signals. Okay, and if you take this portion is the same as, this is what same if you take that, okay, if you take this and if you plot it, then it is going to be like this, right? One second, let me use a different, let me draw the figure and then I'll explain it. And this point is 4 pi by t0 and this point is 2 pi by t0, and this is sy of omega, and this one is for bipolar, and this dotted one is unipolar. Okay, and this one is the main lobe. Okay, let me highlight, this is the main lobe of the sinc square function. Okay, and here I have plotted only for positive frequencies. This is frequency or you can say omega, and here I have considered only positive frequencies. Similarly, if you plot for negative frequencies, you will get the symmetry of that. So I did not plot the negative frequencies here. And the first zero crossing occurs at for unipolar signal at 4 pi by t0. For bipolar, of course, it occurs, the first zero crossing occurs at 2 pi by t0. For dotted line, the first zero crossing occurs at 4 pi by t0. And this 4 pi by t0 corresponds to the frequency of 2f0. So the bandwidth requirement is again the same as that for unipolar signal. Okay, because it has the same width. Okay, I can reduce the bandwidth by a factor of half again by using, instead of half width pulse, this is my half width pulse, instead of that I can use a full width pulse. If I use full width pulse, then my bandwidth requirement will be f0. If I use half width pulse, the bandwidth requirement is going to be 2f0. So if you use a full width pulse, then again the bandwidth will be reduced by half. Okay, this is a maximum one can do, like going from 2f0 to f0. Okay, now let's discuss the properties of polar signal. okay, in relation to the properties of on-off signal. The first point to note is that polar signaling that we have already noted is more efficient. More efficient than on-off signaling. In fact, it can be shown that as far as binary signal transmission is concerned, polar transmission is the most efficient in terms of power, because half of the time you are transmitting positive pulse and half of the time you are transmitting negative pulse. Okay, when you consider on an average the transmitted power, then it will be the minimum compared to the rest of the line coding scheme. Okay, here I am referring more efficient in terms of power efficiency, right? You can talk of power efficiency in digital signals, and you can talk of bandwidth efficiency in digital signals. So here I said the signal is more efficient with respect to power. So power efficiency refers to how much power is required for a given level of performance. How do you say the signal is power efficient? So one can say the power efficiency with respect to the error rate. Okay, so the performance is measured with respect to the error rate. Okay, for certain amount of power, how much error rate I can get it from this particular line coding scheme. Okay, I mean you fix the value of error rate and calculate how much power it needs to transmit. Okay, so if you specify the error rate, you can calculate the power, and different schemes will have different power requirement for achieving that performance. A more power efficient scheme will require less power, and less efficient scheme will obviously require more power. So polar signaling is more efficient than on-off signaling. In fact, it is the most efficient signaling scheme. Okay, we will see other line coding schemes which also has less efficient than polar signaling as far as power efficiency is concerned. But other than the power efficiency, it suffers from all other disadvantages of on-off signaling, right? It suffers from every disadvantages of polar signaling. So suffers all other disadvantages. Okay, so this guy doesn't have no spectral null at DC. Is it good or bad? Spectral null at DC. Okay, if you don't have spectral null at DC means what? You are not transmitting any DC component. That is very good one. Okay, so you are not transmitting DC. Okay, so we have component of DC even though it is not we don't have DC component even though it is not an impulsive form. Okay, so there is no spectrum null at DC, and which is preferable to have because of the AC coupling requirements. Okay, and also we continue to use excessive bandwidth. So this guy needs excessive bandwidth. This is disadvantage and this is advantage, and this is drawback because it needs more bandwidth. And another drawback is not transparent to long ones and zeros sequences. Okay, so the scheme is not transparent to long strings of ones and zeros, and in fact we seem to have one more disadvantages, that we don't have clock recovery components. No clock. In fact, this is a consequence of this not transparent property. If you have a long string of 1 1 1 1 like this, your pulse is always like this. If you use a full width pulse, it will be continuously on. So you lose the synchronization from the received signal. Okay, so no clock recovery component. and moreover it doesn't have any discrete spectral component at f0. So because of that, it's not that much easily, you can recover the clock. Okay, but that is easily taken care of, because if you rectify the signal, for example, if the signal is like this, what is this? In this duration 1, and this is the duration of the pulse 1, this is 1, this is 1, because half of the time this is on, half of the time this is off, on, off, on, off, on, off. Okay, and this is 0, t0 by 2, and this is t0. Okay, so if you have long strings of ones, then we may lose our clock recovery. So how can I recover the clock? Simply rectify the signal. How do you rectify? See, if you extend this, in this duration it is on, I'm sorry, this, in fact, I'm very sorry, this is wrong. This polar signal we are talking about, right? 1 minute. In case, let's say the pulse is, this is 1, and then this is 1. If you have long string of ones, no problem, like this is for 0, right? And for 0, this is on and this is off. For 1, this is on, this is off. For 1, this is on, this is off, this is on, this is off. This is one pulse, second pulse, third pulse, and fourth pulse. If you rectify this guy, what will you get? You will get, no problem, but this negative portion will become the positive portion. Now there is a regular 0 crossing, right? It comes 0. This point, you can recover the clock. Okay. We will convert the polar signal into unipolar signal. This is polar signal, unipolar signal. We can easily convert the polar signal for the purpose of clock extraction into a unipolar signal by simply rectifying the signal, rectifying the received signal, and then generating the components at f0. So in polar signal, clock component is still recoverable through rectification process. In case the next question is, no, before that, this is the half width pulse, right? Half width pulse. In case if I use full width pulse, can I get back or can I recover the clock? This is my full width for 1. If next one comes, again this is full width. Next one comes, again full width. So therefore, 1 minute. This one and again this one, it is continuously 1. In case if 0 comes, then the pulse will be like this, 0, and for next 0 it will be like this. Now if you rectify this signal to recover the clock, then what is going to happen? Positive will be positive, okay, next positive, okay, then this portion will become positive. So in that case it is going to be positive and then it is going to be positive like this. Now can we recover from this waveform? Can we recover clock from this rectified signal? No. Why? Because there is no crossing. The signal stays continuously at +1. How can you recover the clock? No, you can't recover. Okay, as long as your signaling, your pulse is half width pulse, then you can recover the clock. The moment you use full width pulse, then you can't recover. Okay, therefore you will get a clock component once you use the half width pulse. Okay, so if you use full width pulse, there will be problems. That's why we are looking at all these schemes half width pulse, because it is an important function to perform at the receiver. Clock recovery is a very important function that has to be performed at the receiver and also at the repeaters to be able to recover the clock. If you miss the clock, then you can't decode the signal correctly. Okay, so although it is obvious that using half width pulses would recover twice as much bandwidth as using full width pulses, one can always try to use half width pulse because you can recover the clock. Okay, so if you use a full width pulse, we can always reduce the bandwidth by a factor of 2 by simply going from half width pulses to the full width pulse in each scheme. But if you do that, we lose the flexibility of recovering the clock through either directly or through a rectification process. So you are ready to sacrifice the bandwidth. You are ready to use the bandwidth of 2f0. Why? Because to recover the clock. If you try to save the bandwidth and if you use f0, then difficult to recover the clock. So we need to somehow compromise. So we have to keep that in mind. Okay, so that's all about polar signaling scheme. We next go to the third scheme that we discussed. Okay, so how do you improve the polar scheme? Okay, what do you do from polar? We went to bipolar signal. Okay, so let us go to the bipolar, and so the example for bipolar scheme that we said was AMI, alternate mark inversion, and this is also like a pseudo ternary, and that we will discuss in the next lecture. And let me stop at this point. Thank you very much.